So in this video about the integral relations in control volumes, we're gonna discuss the Reynolds transport theorem, which is at the which is behind all the integral relations we will discuss in this chapter. So let me start by writing it. So it reads dBf dt is equal to the partial with respect to t of the integral over a control volume of rho dv, and then plus the integral over the control surface of rho b, and then v minus vc dot n and ds. Okay. So what does it mean? If we look at the first term, that's a change of an extensive property that we are calling B now over a fluid volume. So remember that meant that we're taking a certain amount of fluid and following it over time. Then this term here is a change also of B, but now over the control volume. Remember, the control volume was this volume that we're selecting as our study case. And then finally, this term here is a change of the intensive property B, and recall here that we had, if we write it the other way, that B was the intensive version of capital B, so was the amount of B by the amount of mass. So this is not the change, sorry. This is the flow of the intensive B across the control surface. Remember here that also that BC was the velocity of the surface itself, while little v is the velocity of the fluid. So that's basically what the Reynolds transport theorem says. But perhaps in order to make it more clear, we can simplify it a bit. So let's work with the simplifications. Let's work first with this first term, BC of rho times B times dV. And that we can define as B sub BC, which is the total amount of B in the control volume. Okay, so say if B was 1, then we would have the mass, then we would have the total mass, or something like that. So that's the first one. The second one, we can simplify a bit more. It's the integral over the surface of rho b, the change in velocity, or the relative velocity with respect to the moving surface, dot n and ds. And now say that we have a tube like that. Say these are solid walls. Here as well. And we're basically having our fluid here, and that's our control volume. Now, this integral then, what we can say, this is the integral over the wall, so over this wall here and here of the same term, plus the integral over the inlet of the same term. Now if we're assuming the flow is going in this direction, the inlet would be here. And then plus the integral over the outlet of, again, the same term. And the outlet, in this case, would be here. Now, if we look at the velocity here at the wall, since it cannot be crossing the wall, the velocity is going to go something in this direction, and it's going to be tangent to the wall. So the wall has a normal here in the velocity because it's not crossing, it has to be tangent. Then of course, we know that the dot product between a vector, between two vectors that are perpendicular is 0. So in general, this whole term is going to be 0. So we're only going to have the inlet and the outlet. Then furthermore, if we look at the normal vector here at the inlet, it's going to go in this direction. And you can see the velocity is going in one direction. It's going inwards. The normal is always pointing outwards. So this dot product is going to be negative. So in general, this term is going to be less than 0. And finally, we look at the outlet. We also have this, this vector, but now it is clear that the normal is pointing outward, the velocity is also, so the dot product v dot n is going to be positive. So this term here is going to be positive. And what we will do is actually label this term as minus b in. So we are taking into account already the minus sign, and this one here, we're going to call it b out. So therefore, this integral over rho b, again v minus bc dot n, and ds, is going to be equal to minus b in plus b out. And then in some cases, we will even be able to simplify it further and have it as mass in times b in with a minus, of course, and then plus mass out plus b out. And I forgot the dots in here. And when is this true? It's only when things are constant. So b, mass, density, velocity are constant. And of course, I mean constant on the surface, so either constant in the inlet or constant in the outlet. Okay. Otherwise, this is always true, this part here, but sometimes we'll have to do the integration. So if we go back and write the simplified version, we'll have that dBf over dt is equal to the change of this extensive property within the control volume over time, and then minus b in plus b out. And that's again, b in is the amount of fluid flowing, so coming in the inlet, and then b out is the one in the outlet. And actually, if we want to be a bit more general, we can write it with these summation signs, and that means we sum over all the inlets. So in many problems, we will only have one inlet and one outlet, but in some of them, there might be different ones. And basically, this chapter is going to be using this Reynolds-Transport theorem in different situations in order to obtain these conservation laws. So for example, if we look at conservation of mass, then the extensive property is going to be mass, and the intensive property, well, it's going to be mass over mass, so it's just going to be 1. If we look at the energy, the extensive property, again, will be energy. We will define it. And the intensive property is going to be E divided by mass, which we will call the specific energy. Finally, if we look at momentum, momentum is going to be defined as mass times velocity. And then the intensive property is going to be, again, momentum divided by mass, so simply the velocity. And the conservation of angular momentum is going to be mass times r wedge p. That's the angular momentum. We will define it more carefully when the time comes. And again, the intensive property is going to be that divided by mass, so simply r wedge v. So that's enough about the Reynolds transpose theorem.